So far, our models were generative. What do I mean? You were either predicting the next word and you had a few options, maybe 50,000 options. That's the size of your vocabulary for the next subword. Or you were masking part of your input and then you were asking, what did I mask? And that one was also generative. The model is going to give you a probability distribution on top of the mask token as the output. And then you have the option to sample any of them, but we usually pick the maximum probability one as the word that was being masked. So all of them are generative. Can you approach this problem using a discriminative approach? And by discriminative, I mean, if you have two images, the question could be, is this a cat or is this a dog? And then you are discriminating between the two. Here is the same thing. I'm going to tell you how you can introduce discrimination inside a generator model for the task of pre-training. So far, we were doing mask language modeling or next word prediction type of tasks. But for mask language modeling, BERT type of approaches, this is what ELECTRA is going to be based on. You are masking 50% of the tokens per each sentence or per each sequence. And then you're going to notice that if you start pre-training, a BERT model is going to take a lot of iterations to converge. Because usually 15% of the tokens are absent and you're learning from the rest of the sentence and you're being wasteful. Most of the information in the sentence, you're just throwing it away. Or 50% of it, you're just throwing it away. That's the motivation for using a discriminative approach. What does ELECTRA stand for? It stands for Efficiently Learning an Encoder that classifies token replacements accurately. So that's ELECTRA. What is the idea? You have an input sentence. The chef cooked the meal. We are still going to do some masking. We mask there, for instance, we mask cook, and the rest of them we don't change. There is going to still be a generator, and this generator, you can think of it as a transformer architecture, transformer encoder. But what did we change? Previously, on top of this mask, you had a loss function immediately, and the loss function's job was to generate the next word or generate the masked word. What did I mask? And then the answer was there. Or on top of this mask, what did we mask? And the job of the loss function was to penalize the mistakes. We are still going to do the same thing, but we are going to keep the generator small. And if it is small, it's not going to be capable to solve this task perfectly. So it's going to keep making mistakes. For there, perhaps it was simple. It's going to give us there. For cooked, perhaps it was a harder word to predict, and it's going to make a mistake because the model is small. It doesn't have the capacity to fit the data really good. So it's underfitting because the model is small. This is the other extreme versus overfitting. This is underfitting. Okay, the generator is going to generate a sentence. It's going to be a messed up sentence. And this is where ELECTRA is going to come in. You have the encoder part of a transformer. This is going to be a giant model. And its job is to look at every single word and say, is this a real word or is this word replaced? So it's the story of being real versus fake. And this idea of real versus fake, we are going to see that over and over again when we do generative adversarial neural networks, when we do GANs. And the job of the ELECTRA is to say, is this real? Is this fake? Okay, perfect. Mathematically speaking, let's be more rigorous. You have G, your generator. You have a discriminator. You have an input sequence. In this case, the chef cooked a meal. You take your input sentence, and then you can pass it through your small BERT here, and it's going to give you a sequence of tokenized vector representations. And H is exactly this encoder here. That's your generator. Or in particular, it's going to be HG. A sentence goes in, a vector or a sequence of vectors is going to come out. You're going to look at the teeth location, which would be this location here. There is a corresponding vector. Then you have an embedding for the word cooked. You take that, multiply it by, so you take this embedding vector, multiply it by the outputted vector. You exponentiate it to make it positive, and then you divide it by a bunch of other exponentials of all the other possibilities for the words. And this is how you're going to get a probability distribution out. And this is what we have been doing. And as I mentioned, this is the token embedding. You have a token, you embed it, you vectorize it. For the discriminator, its job is very simple. It's going to look at one of these words or the corresponding vector coming out of the discriminator on top of that word. You're going to multiply it by a matrix, and this matrix is going to take you, or it's just a vector. It's going to take you from dimension perhaps 768 to dimension 1. And then you push it through a sigmoid, that's going to give you a probability. And this is the probability of this token being real. The other probability, the probability of this other token being a replaced one, being a fake one, is going to be 1 minus being real. So it's enough to model only one of them. How do you mask? You pick a sequence of masks. These are numbers between 1 and n, which are basically telling you which one of these words to mask. You're going to pick 15% of them. And then these MIs are sampled uniformly at random from numbers between 1 up until n. And it's basically telling you mask the second entry, mask the third entry, mask the first entry, and so on. And then you're going to just mask them. You have X, you have M, which is your set of positions that you want to mask, and then you are going to replace those positions with a mask. And this is what you have here. An X mask is the entire sequence. And then you can call your generator, which is going to give you the probability. And then you can sample from that probability. And this is how you're going to get 8, for instance, here, and then you're going to get there here. In the next step, this corrupted version of your input is going to take as an input, it's going to take X as an input, it's going to take the mask positions, and in those positions, it's going to inject the mistake or whatever the outcome is out of the generator. For instance, in this location, it is injecting 8 rather than a mask token. Now it's time to write down your loss function. You need to train your generator. You're still going to train it using mass language modeling, which is maximizing this probability or minimizing the negative of the log of that probability. You still have that. You are adjusting the parameters of your generator, but your generator is a small model, it's going to learn quickly. But because it's a small model, regardless of how hard you try, it's going to underfit. It's going to keep making mistakes. And those mistakes are going to go in your discriminator, whose loss is increase the probability of the correct outcome. And the outcome could be either this token is the original token or it's a replaced token. And this is just taking that into account. If the corrupted one is actually equal to the input, in this case, there is equal to there, you need to maximize the probability of the corrupted token being the original token. So you're maximizing this probability. Otherwise, if the corrupted token is not equal to the input token, you are making a mistake, and you need to increase the probability of that mistake. You need to say, yes, this was a mistake. And the probability of being a mistake is 1 minus probability of being correct. We are going to see this loss function again when we do GANs. But is this clear so far? Okay, perfect. How does the model do? It's going to end up being an efficient model in terms of flops. This is glove, this is Elmo, this is bird. For the same amount of flop, ELECTRA small is giving you a better glue score. For bird base, ELECTRA base, having the same size is giving you a better performance. For the same number of flops, ELECTRA is doing better. And then that pattern keeps going on. And then at some point, you are going to match the performance of X and net. But let's zoom in, or actually let's look further into the future in terms of flops. This window here is exactly this figure. So that entire figure is a subplot of this other figure. So up until this point, you had 8 times 10 to the power 20 in terms of your flops. Now you're increasing the flops. And this is actually where Roberta, and XNet are living. So they're much more costly models. At a much lower cost, you're achieving the performance of XNet. And whenever you hear this word replaced token detection retraining, this is what is happening here. The replaced token prediction. Which token was replaced, which one was real. And the other one is comparing to BERT, two-stage, ELECTRA, adversarial ELECTRA, and ELECTRA. And then you can see ELECTRA is doing better. This is one of those systematic studies. You have these options. For two-stage, in the first stage, go ahead and train your generator. In the second stage, train your discriminator while fixing the generator. That's two-stage. Adversarial ELECTRA has only the adversarial loss. It doesn't have that masked element loss. And ELECTRA is having this loss exactly. Yeah, I think it's a good time for me to stop. For those of you who have questions, I'll be around.